So, Professor Furfaro, thank you very much for your time. I'd like to start talking with you about your experience in the Osiris-Rex mission, what you did in that mission, and what was the main results, the main outcome of that.
Yes, okay. Thank you for this talk. Actually, it's a pleasure to discuss with you, especially as part of the Stardust network, which is an exciting endeavor. So, yes, I worked on Osiris-Rex as a faculty, actually, at the University of Arizona in the mission for about 6 years. I was involved in the concept study, right? Mm-hmm. And just to remind everybody, Osiris-Rex is the third New Frontier missions, and the New Frontier program is a NASA program that they fund what they call the medium-class spacecraft explorer, order of $1 billion.
Medium class is referred to the kind of spacecraft.
The kind of spacecraft, also kind of missions overall, right? For example, the smaller class is Discovery. Program is about $500 million. And there are something else smaller, like Simplex, where it's about $50 million, which involves CubeSats at lower scale, like $15 million, and so on. Anyway, there is all a set of programs for the exploration of the solar system and NASA that are competed. They're usually PI-led mission. What it means that there is a PI who's assembling a team. Usually you need a spacecraft provider, you need a NASA center to manage, you need instrument providers, you need a science team. A PI usually arranges and leads the whole team. That's what we did at the end of the University of Arizona. When I got involved, we were selected for phase A, basically step one. We passed.
When was this?
It was 2010, right? And we went through a 10 months concept study, which is equivalent basically to a phase A concept study. And we were competing at the time with the other two missions that were coming from Jet Propulsion Laboratory. One was a Venus mission, Venus lander, and the other one was a South Pole moon sample return. Okay. And then eventually I got involved in this concept study. We went through 10 months of refining our concepts, our cost models, and we basically wrote this concept report. We went through site visits, where it's a full day where the NASA review team comes down and you have to present pretty much your finding and what's your approach to it. Eventually in 2011, I think it was June 2011, it was selected. So we got the announcement that out of the 3 missions, Osiris-Rex was selected to move forward as in the New Frontier program, and then eventually we had the bridge phase, and formally in November 2011 we started phase B. Okay, so we got selected 2011, and we eventually launched the spacecraft September 8, 2016. So we had a typical 5 years development phase. During this phase, I had different roles, right, depending on the needs. The major one that I got was I was the system engineering lead for the Science and Processing Operations Center for the mission. Basically, I was responsible to developing all the architecture and requirements for the data processing and product, basically generation, as well as the science commands associated to the instrument commands planning associated to the mission. I also served as ground system engineering, so a little bit hyper role, basically connect all the ground infrastructure, which was comprising 3 elements. Basically, one is what we call the SPOC, the Science and Processing Operation Center, and it was the flight dynamic systems, and there was the mission support area, which is the operation, the commanding of the old spacecraft for operation at Lockheed Martin in Colorado as part of the ground system. So it was an exciting experience. It was it was one of these complex missions that was extremely challenging to fly, and eventually now still at Bennu, the asteroids. The team is going to attempt grabbing the samples sometimes this summer. It's going to be challenging because the environment is extremely uncertain, because from the United States perspective, it's the first time they will fly around and operates in what we call execute basically close proximity operation around a small object like Bennu, diameter 500 meters. And we are targeting now an area of about, for sampling, of about 10 meters diameter, which is honestly much smaller than what we originally had designed the spacecraft. Right? The original.
And why did they change? Did you change these requirements?
Well, formally, before launch was not changed. It was still the spacecraft designed to that, to designed to target an area of 50-meter diameters, right? And basically, this area, that was the capability of the error, let's say, ellipse for what we call the touch and go maneuver. So remember, we don't land on the asteroids. What we do, we touch, grab the samples, and go away. And the touching phase is only 5 seconds, okay, estimated. So it's a very peculiar operation and challenging because it's in a very uncertain and a very low gravity environment. And the original idea was that the morphology of and the geology of the surface, the Bennu surface, would be completely different than what we eventually expected. But that's part of the also excitements of space mission. It's an exploratory mission, so you are not sure what you're going to find. You do your best to design the mission to the most up-to-date information that you have. So we expected an environment, a geological environment, much closer to the one on Itokawa, found by Hayabusa 1 mission, in which there were large areas of small, fine regoliths. And
why is that, and not, for example?
It's not the case. Well, part of the problem was associated to the fact that we did an indirect estimates of the thermal inertia associated to the asteroids by measuring through the Spitzer telescopes a few years back when the asteroids came closer to Earth. And the thermal inertia seemed to indicate that there would have been a smoother area associated to that. Unfortunately, as I said, many of these measurements might be ambiguous. It's really hard to unambiguously reach conclusion. Also,
how does it work, the measuring of
well,
thermal inertia?
Basically, you measure the thermal flux, right, of the objects. And through the thermal flux, what you do, you try to back out the thermal inertia through a thermal model. Okay, so it's model based, but then you have to do something else to go from thermal inertia to grain size. And that's where things get extremely hard, and the model, you're solving an inverse problem, right? From measurements, you go to physical properties through a model-based approach. This inverse problem are nominally are known to be ill-conditioned, right? So it's extremely hard to find, a reliable, solution. So, and also because the class of objects of Itokawa and Rio and Bennu were similar, so we expected also from the information that we had from the ship model, which was it was radar based derived, with the 7-meter resolution, the original one, seemed to indicate also concentration of regoliths at the equator. So the bottom line is that we did the best. The scientists did the best, and the surface, seemed to be much rockier, rougher. Important.
So you need to shrink to get.
Yeah, you need to shrink. We were not able to find the 50-meter area smooth enough that is scientifically interesting, but then the science became at this point a lower priority with respect to the safety of the spacecraft. For the safety of the spacecraft, you need, for example, to find an area relatively boulder-free. You need to find an area where the slope is less than 14 degrees, which is the basic tipping point that the spacecraft during the touch and go is able to tolerate. And then also you had to have some reflectivity associated during navigation for LiDAR. And so there were all these constraints, and it turns out that anyway there were such limited areas. Not only that, actually it's safeable, it needs to be safe, but also sampleable. To be sampleable also means that you have to have fine regoliths with the grain size or pebbles not larger than 2 centimeters in diameter.
Because you need to, how does it work? You push.
Yeah, basically it's an arm that is extended. It's about 2 meters, and at the end there is this TAGSAM. It's a sample acquisition mechanism. Looks like a filter, air filter of a car, right? But there are basically 3 nitrogen bottles associated to that, and when the surface is touched, right, it's sensed through an accelerometer. Basically, the accelerometer triggers the bottle of nitrogen. This gas, it's called gas, is shoot through the mechanism into the surface because of the low gravity. The idea is that to mobilize the surface, eventually there is an opening that collects all this regolith with the diameter less than 2 centimeters, then close it, right? And it can acquire as much as 2 kilos of material. Okay.
And how fast is the spacecraft going down?
So the requirements, this was designed, it was no more than 10 centimeters per second vertical velocity and no more than 2 centimeters per second lateral velocity. So those are the constraints, and usually you are in a free fall from about 50 meters altitude.
Okay, so
you're going down.
Stop control. I mean,
yes,
it stopped itself because it's going to be autonomous, even the navigation.
Well, so the nominal plan, which was when we designed the whole touch and go maneuver, it was supposed originally to be with pretty much open loop, which means ground in the loop. Okay. And what it means that the sequence of commands, right, or barns that are executed during the mission are really pre-planned from the ground, uploaded to the spacecraft, and then executed according to a certain time, right, clock. And it consisted basically, so the spacecraft would be in a safe home which is a polar, terminator orbits, about 1 kilometer altitude, not altitude, 1 kilometer's radius orbit, so about 700, meter, 750 meter altitude. You execute an initial burn. You coast for quite a while. Eventually, when you are 125 meters, to go, you execute another burn. Once you are about 50 meters, you then do the last and final burns that basically match the angular velocity of the asteroid, and you go as vertical in a coasting phase. Once you touch the surface,
as soon as you touch, there's another burn.
Yes, it's after 5 seconds, right? Usually estimated. Then there is another burn that will bring you far away from the asteroid, talking about a few kilometers, where you can do safely some measurements of the sample, to estimate if
you got something.
You got something, right? It turns out that the way we measure those things is by basically doing the slew maneuver around one axis, right, before and after the sampling. Basically, what you're measuring is the difference in moment of inertia, and there is a sensitivity of about 60 grams, 50-60 grams. So we expect to get as little as 60 grams, as much as 2 kilograms. 2 kilograms. So, and you have 3 attempts, right? If after the first touch and go, you do the measurement, you see that you're below 60 grams, that means you're in uncertainty measurements, then you have to go back. Of course, even there it's going to be probably depending how close you are to the 60, because then you have a trade-off of risk versus reward, because at the end of the day, executing the maneuvers over and over, it increases the overall risk, right? So the nominal approach is completely ground on the loop, right? Eventually, we put some level of closed loop or feedback into the system by measuring using a LiDAR to measure the limb, the crossing, which give information about the range to go, and another measurements of an altitude at a certain point that will eventually provide some onboard correction of the timing of the burning and the length of the burning. So you can, based on that information, the range to go in one altitude, you can correct the next two burns. But even with that, it's been, when we did the initial Monte Carlo analysis, we're meeting the 50-meter requirements, right? And sometimes we will go to 20 meters requirements on the equator, okay? However, now the selected area, by the way, the process was to down select after the orbital B phase, down select 4 sites, right? Eventually, one was recently down selected. It was a couple of months ago, called Nightingale. Nightingale. That's a name of. There were fancy names for the team assembled for all the 4 sites. Eventually, Nightingale was selected, and now it's going to be the challenge to hit these 10 meters. I know that eventually there will be some additional level of autonomy in terms of navigation, with some level of feature tracking, using the images. But originally it was supposed to be a backup option, but now I think it's going to be more and more increased. So we'll see. We're crossing fingers because it's going to be really challenging. The surface was definitely. We had the hint of that actually after we saw the first images of Ryugu from Hayabusa 2. They didn't expect anything like this as well.
How was the timing in terms of? So while you were working in 2010,
they arrived a little bit. They arrived a little bit earlier.
Okay.
And actually, as a matter of fact, they already collected the sample in November 2019. They departed for Earth. So their mission was that's Hayabusa 2. So they arrived before us, a few months before us, and they already departed. So it's been about a year. Yeah, and I have to say that the concept mission between the two, they are much different. They have much more autonomy, and also, for example, they are exploring by executing hovering, right, at a certain altitude, and then move around. We don't do any hovering. We do both orbiting, then we do hyperbolic arcs back and forth. Okay, so that's kind of it's conceptually different, the two missions, two philosophies. And what happens is actually the Osiris-Rex origin, when we proposed it, we convinced NASA to fund us because we did quite a bit of work to address the pitfalls of Hayabusa 1, which was, lesson learned. One of the big deal from us was lesson learned from Hayabusa 1, trying to make our mission successful.
And was Rosetta?
Well,
there's nothing to learn from there.
There's always something to learn. The problem with Rosetta was a much longer scale mission, and I think it was launched 2006, if I remember correctly, right? At the time, Osiris-Rex was just a concept, not even proposed. It was at the time, I think it was just barely proposed for Discovery, for the Discovery program, but at the time it was not even called Osiris-Rex, it was called only Osiris, because it was a smaller spacecraft with a much smaller science scope, and simply because it was a $500 million mission originally when proposed for a Discovery program. But when proposed eventually didn't get the Discovery, and we went to a scale up to a mission, a New Frontier mission, that you're talking about extending, having much more many more instruments, and extending what you can do in terms of science objectives. Yeah. So.
And now, are you still working on near Earth objects, asteroids?
Yes, actually, I was on the mission on Osiris-Rex until launch. So I went through all development phase, and I had students now also working until pretty much last year on the Osiris-Rex mission. My involvement, however, after pretty much October 2016 was over, I moved to do a few other things. In terms of missions, I'm actually now leading part of the investigation team for the newly approved NASA NEO Surveyor Mission. Okay, formerly known as NEOCAM, right? Now it's been approved as part of the what we call the Planetary Defense Program. So it's not a science mission anymore; it's a survey mission. It's part of the Planetary Defense Program. It's interesting because those missions, while the science mission like Discovery and New Frontiers and so on are PI-led mission, the planetary defense missions are not PI-led, but we have, at the University of Arizona is the lead in the sense that we have the surveyor director. That's what the name is called. Okay? It's equivalent to a PI, principal investigator, that's called survey director. And instead of the science team, you have the investigation team. So what is this mission? First of all, so we understand also the structure. This mission is an exciting mission. We are launching by 2024 a spacecraft to the L1 Lagrange point between Earth and the Sun. And we look basically with the we look orthogonal to the direction of the conjunction Earth-Sun, right, because we don't want to point at the Sun, with an aperture of 120 degrees on each side. And we, as a requirement, we want to map greater than 90% of all Earth, near-Earth objects with diameter greater than 140 meters. Okay? So basically, we're gonna just identify and characterize all the objects, or greater than 9% of the objects that can be dangerous for Earth.
How do you know when you reach 90% of the total?
Well, we know because there are part of the investigation team. There is the asteroid population models, right? So we have information about what we expect through this model, how many asteroids we are expecting to see. And there's of course some uncertainty there, but that's the way that you do it. So we have a population model that we know the distribution of all the parameters based on information, the best information we can get. Right. And actually we use it to do simulations of the mission to know that, what are the limits of detection and things like that. It's very exciting. What I'm doing there, I'm leading what we call, as part of the investigation team, what we call target follow-up working group. Basically, we are in charge of developing an artificial intelligence system that can process the data as acquired from the mission and rank all the asteroids, and also figure out autonomously which one are the most important to follow up, either from the NEO Surveyor spacecraft or from ground observation systems.
And it's going to do it in terms of how big they are, how risky.
Yes, actually, we're designing the tools. Actually, the tool is actually as an intelligence system. It's a cognitive system. It's based on Bayesian and fuzzy, combination of Bayesian and fuzzy inference. Okay, so it reasons over the data and take conclusions. And of course, we have some input parameters that are derived from the observation. That, for example, tells you some information about the diameters, about the MOID, or the minimum intersect orbit, and of the predicted orbit. We put also information about probability of impacts, right? And information about time of impacts based on the best information that you have at the time. The reason why you needed to do it autonomously is because, especially at the beginning of the survey, we're expecting that per day a discovery rate of 1,000 or even 1,000 or to even 10,000 per day. There's no way that the investigation team will look every day in details at this one and figure out if it is dangerous or not, or what's the rank of this. So the system will reason on that, and then eventually will task more observations so that we can better characterize and track the objects. Because of course what's going to happen is that once you detect and you observe, what you do, you define those what we call in jargon tracklets, right? Which are partial arcs of the system that then can be correlated to a definition of the orbits. But there's a lot of uncertainty because of the propagation models, or because there are also uncertainties in terms of understanding exactly what is the orbit, unless you continuously observe for a while. And so anyway, so it's a very exciting thing to do. And this tool is basically going to code expertise from different planetary scientists into a system that will try to reason as that. We have a record. I published papers that promoted this idea of designing cognitive systems that can reason in a certain environment for space explorations. Right. The idea was to have to basically mimic the way planetary science thinks about the exploration in the general terms, but this is now adapted to the problem of is it important. And this tool is extremely important also because the spacecraft has a survey pattern, right, that is pretty much established, more or less. And of course, anytime you want to observe some object from the spacecraft, you have to somehow go from a survey mode into a targeting modes. And that disrupts the pattern of the survey, which is a resource, of course. And so it's kind of one of those things that you want to try to minimize the impact on the overall survey because it might affect the discovery rate and so on, and rely when possible from ground. But this is going to be all reasoned on depending on the type of objects, depending on the status and availability of the ground assets that's going to serve.
So autonomously from the ground, this intelligent system is going to tell the spacecraft when to switch from one mode to another.
It will provide the information about, what to do. Of course, this is going to be provided to the operators. It's going to be, quick turnaround. That's important because to process all these 10,000 objects,
Okay. So. And do you see applications of this also for space debris?
Yes, actually. As a matter of fact, not just for also just with space debris, but we are also talking. University of Arizona is also lead in ground-based discovery of asteroid discovery. There is a survey called Catalina Sky Survey, which is basically part of the Lunar and Planetary Lab. And I think since 1995, we discovered of all possible sites 50% of the known objects. And very interesting these tools also on their own because they want to also minimize or increase the autonomy, the discovery and the discovery rates and these kind of things. And of course, yes, for space debris, now things that is happening is that I'm also director of what we call Space Situational Awareness Arizona. It's an initiative where we work with different players, mostly Air Force Research Laboratory, to basically characterize the behavior of space objects, right? Which includes space debris, right? And so one of the problems is tasking, right? Telescope tasking, which might fits the bill, right, for this autonomous system. But we're also we're developing the cyber infrastructure where telescopic data, we're mostly now working with optical assets that we have, can be processed in real time, and then went to autonomous system like deep learning based system that can take light curves or astrometric data and give you information about what the object is doing. What is it? So we want to identify, characterize, that is classify, and also understanding behavior, which is a complex problem, right? So we're working in this regard to advance the state of the art. So there is kind of a tangent between planetary defense that we're doing work, space situational awareness work, and also implication for space debris, potential traffic management, so on.
Okay, and how do you decide? Now you mentioned deep learning. Previously you said vision-based, cognitive-based systems. How do you decide which one to use?
Well, so I think it depends on the problem, okay? Maybe we'll talk later, but I'm a very much big proponent of deep learning, deep reinforcement learning, also what we call now deep reinforcement meta-learning. So those approaches are all data-driven, right? It can be also physics-informed, but generally the idea is that you have a bunch of data, a lot of data, and then you want to infer information from the data. In the case of, so if you have enough data, you can train a system, right, to autonomously perform certain tasks, which could be exactly the follow-up idea. However, in this case, we have a lot of knowledge from scientists, right? But we don't have, at this point, a lot of data to train on. Okay, I mean, we do have different data from the minor planet centers, right? But it will take, in our opinion, at this point, it will take quite a bit, to create proper data sets that can eventually inform. So we're working informed deep neural networks to do the job. It's not impossible. We took a little bit different approach simply because we leverage on the fact that we have an investigation team that's been working on this for a while, and then now, and usually when you work with scientists, planetary scientists, or asteroid scientists, or NEO scientists, they usually would like to understand what is happening and why you get certain answer, and so that's important for the community, right? And in this specific problem, a cognitive system works better because also they are explanatory. So if I reach a conclusion, I can also provide the system can also provide an explanation of why you reached that conclusion. Deep learning systems do not do it. They work on the data and autonomously learn information from the data, but the knowledge is distributed across the weights of the networks. They might be more powerful, but they might not fit they might have a disadvantage in a situation where scientists are currently interested in understanding exactly why I'm getting that answer. Again, there was a choice that was made based on the fact that our team has experience both in deep learning and cognitive systems, right? I found that whenever you work with planetary scientists and space mission exploration, where science or anything like planetary defense is in the is the central team. The science team plays a major role, and explanation plays a major role as well. Therefore, this system, I think, are better suited to interact and with so it's very much a blending of domain experts in the realm of computer science or computer engineering and the planetary science, which might fit very well for the case being.
So both cognitive-based systems and meta learning are based on the same philosophy that since you don't have a lot of data, you want to use already the knowledge of the way in which you learn from data to build something even more abstract.
Right.
Is the physics-informed method similar, if this is true?
Well, so we have to make a clear marked distinction, and the distinction is the fact that even if you work, so first of all, what is meta learning? So you mentioned deep learning. I mentioned deep learning. We also mentioned meta learning, right? Or meta deep learning. So meta learning is a little bit of different concepts. Meta learning literally means learning to learn. So you want a system that not only learn the task that you want, but also learn how to learn other things. And usually those systems are trained on distributed set of tasks. But from each task, he learns, he accumulates experience, and then eventually he can adapt quickly to new coming tasks. So as a result, you have much less data needed to train these things. Okay, that's the principle behind it. Nevertheless, it's still data driven.
Okay,
and it's still unexplanatory, right? So the only thing is that the meta learning mimic a little bit the learning process in humans, where we don't need tons of data and tons of iteration to learn something. We learn very quickly, and the reason is because we probably learn on many tasks, and we take with us the experience that we learned on other things before, right? The cognitive system needs less data simply because it incorporates knowledge extracted from the domain scientist. So what it means that basically I have to elicit knowledge, which eventually to design this tool we went through pretty much interviewing. I'll call it interview, but there's been an open discussion with planetary scientists that tell me how the process of inferring which one is best versus the other goes. And so it's an interactive process where you work with the scientists to elicit their knowledge and try to put it in a cognitive system that does the inference as the scientists do.
And they never see data, these systems. I mean, when they're ready, they don't need to.
When they're ready, no, it's another interesting thing, an interesting flavor. There are different flavors here because things, to a certain degree, at a certain point becomes hybrid. Depends how you design this. At the beginning, no, you don't need data. But nevertheless, when we have a plan to do test and validation, so for example, build our own internal simulator tools where we can run simulates observation of many asteroids, right? With known parameters, right? And given these known parameters, if you give it to a scientist, he will tell you, I think this is most likely to be better than the other, or to be more important than the other, or this is the probability that I think that's more likely to be, dangerous than the other. And we want to compare, we do cross-validation in the sense that the system will need to reach the same conclusion than the scientists do, right? If not, you have to tune internally some parameters, right? Some weights or some inference parameters that play so that the two things are matched. However, if you have some data, even limited, in this case you don't need it, you can also tune the system based on data that maybe are labeled by the scientists. That's another possibility that we're also exploring. In this case, you can still train the system, but the training happens to train in the sense that you train the parameters that are behind the inference systems as defined by the scientists. Okay. It's an hybrid approach.
And will it keep the transparency of the system?
It still keeps the transparency because nevertheless it gives an explanation if you tune it.
Okay.
Right? And then it's very interactive because you have to cross-validate with what happens with the answer that the systems do. Mm-hmm. Indeed, basically, one thing that we did is, we made up some 100 objects, right? And somebody gave me out of the 100, it's not 100, sorry, we put something like 990 random objects, right? Random NEOs with certain characteristics and so on. And then, embedding this, scientists gave me 10 dangerous ones. And they told me, this is what I think is the most dangerous. And then see if the system picked them up out of it. It turns out they did, right? After some tuning, we had to do some tuning because the beginning, the explanation didn't seem to be consistent for a couple of those. Most of them was, a couple of those were not. And then we started looking at that, why is this system thinking that they're not important? So it turns out that eventually when you account for the fact that maybe the ground system was able to see it, right? Mm-hmm. It will give them lower priority versus others that instead were not seen by the ground but seen by the spacecraft, because we waited on the way we gave the system to inference that usually it's better to give highest priority to objects that cannot be seen by any ground assets, but they're only identified by the spacecraft. So as you see, that's a kind of a process of validation. And then we had to tune it, a few things. So it's kind of an iterative process to go. So the other one is completely data-driven, but for a deep learning to work, we'll need a lot of data. At this point, it doesn't seem to be the best way approach. But as we say, we have time to develop this. So we're in the testing phase. We are the development phase now. So.
I see.
Yeah.
And I have in mind a really abstract question
Yeah.
about this. So you said that we're gonna track 90% of the NEO objects.
Yeah.
Do you think we have enough time to avoid a dangerous collision? Dangerous in the sense that it's gonna kill.
Well, it depends. It depends. Again,
how much effort do we?
Well, no, it depends how far away is the object, right? If it's gonna collide or not, right? It depends what we discover. If you ask me, do we have time to react? The answer is unfortunately, we don't on a 6-month scale or even a year scale. We just simply don't have anything to. We don't have a proven architecture that we can deploy in a few months to go and do something to avoid the system. If the time of collision is less than a year. Okay?
Because we can just give a little push the asteroid.
Well, it depends. Again, it all depends. What's the trajectory, right? There's been studied. There's actually Iowa State, the Asteroid Deflection Research Center led by Bongui, did quite a bit of case for demonstrate technology that can be deployed potentially in less than a year to go and intercept an asteroids and do something with this. His proponent was about using the nuclear devices, and he did quite a bit of studies on that, on the architecture, how you could do that. The first thing that he realized, actually they work with the Lawrence Livermore National Lab. They use hydrocode to simulate explosion of material. And they found out explosion of nuclear devices on asteroids and see how you would disrupt this. And he found basically that if you put this on the surface, it's not going to work. You have somehow to put a hole into this and inside, and basically explode this nuke from the inside. That's the most effective way. Of course, it all depends how far away you have to have some time, depending what is the time to impact, time to predict the impact. But so, however, it was not his architecture was not like, oh, go on the asteroids like Armageddon styles, drill and put it there. No, his architecture was mostly hit it, right? Hit it, and as you hit, you explode the device. However, there's a lot of challenges there. First challenge is that the velocity, impact velocity, was the order 10 kilometers per second. You're talking about that's how fast you go in a typical intercept. They did some simulation, for example, for the Apophysis case. Mm-hmm. So if you fly 10 kilometers per second, the first challenge that you have is GNC, especially the navigation part, because then if you have something, a diameter of the order 150 meters, it's extremely challenging, to have a system that can acquire the spacecraft that is a second before impact, you are 10 kilometers away. That's extremely challenging, right? So the first thing is to navigate in a way that you basically correct it, right? So that you are guaranteed that the interception. And 140, 150 meters, not that much in terms of size for intercept. That's the first challenge, but they developed some technology, demonstrated what can be done in a missile-like system, using thermal, infrared, detection and so on. The second challenge is the fact that if you have a nuclear device for detonation and you hit it at 10 kilometers per second, the device won't work. They can sustain impacts of the order of 300 meters per second at the most. Okay. So what do you do?
So what does it? So the bomb, let's say,
won't explode. Okay. If you're damaging the bomb, basically.
Okay. You destroy the bomb without
destroying the bomb. Yeah. Explode. So you want. Okay. You will have an impact and some explosion, but you're not gonna have. It's not the same that putting a device and exploding. Okay. So you're damaging.
Exploded right before.
Yes. Okay. So but the problem is the study that they did is that if you explode right before, what happens is that it's not effective. There is some effectiveness, but you won't, depending on the size, it won't be able to break it to a point that if you are far away, the fragments will disappear, right? Because what is happening is that if you explode it completely from the inside or some level of inside, you're going to explode and generate a cloud, and this cloud eventually will disperse. The center of mass will continue, but and if you're far away, you'll avoid the Earth continue. So he had proposed an architecture where you have he had two architecture. So this is, again, keep in mind that I'm reporting works, it's not mine. So I'm just going by memory. But basically they had an architecture where they had two spacecraft, one after another, and there were two options. The first one hit the surface, create this hole inside. The other comes right after. You have to be precise to hit the same hole, and then time the detonation right before it impacts to explode. The second one, architecture was the same, but the two spacecraft were connected through a long truss, right, system where basically the first impacts, then it crashes, and then as you go, you tune it. Yet it's a challenging problem because you're talking about high speed and extremely precise timing. So NASA funded one of these phase 2 NEAX programs, about $1 million to do the study. They went through the whole, I would say, concept study architecture. But then, again, there's no program currently that can fund a tech demo for these kind of things. What it means, as a result, if something hits us of that size, we're pretty much unprepared in terms of going and deflect the asteroids. So that's on that time scale.
Okay.
If it's a 20, and part of the problem was the fact that, planetary defense for now, at least from the NASA perspective, is more survey. And the idea is that if we map out the time of impacts, and we found out that the time of impacts is 20 years, we have 20 years to prepare. And maybe it's not going to happen because you have some probability that this will happen anyway, because you don't have the ability to predict all possible, the exact trajectory is in 20 years. Time scale.
Also, you don't have 10% of the existing, if
yeah.
you map 90%, we still have 10%.
Right. So what happens is that there was in the community, the planetary defense community, there was a prevalence of survey methods versus active intercept or active removal of the threat, because the idea was that the bigger one, let's say larger than 1 kilometer, were all mapped out and they were ruled out for intercept, or the intercept, the probability of intercept, high probability of intercept would happen in 20 years, 30 years, 100 years. And the idea is at the time if you can do something later on, if this really happens. I remember a while ago people were working on the tractor idea, asteroid tractor idea, where you would go there and just basically use the small gravitational pull, to slowly, divert it, and the delta V would be very minimal, but on a longer scale would do it. So people have been proposed different solutions, but there's no actual program that can show that this technology, we know how to do it. We know on papers how to do it, but then it's different than say, I want to do a tech demo to go there and intercept, deflect as well. Deflection could be an effective way, but I'm talking about without any kinetic impactors, not nuclear device-based impactors. It could be effective, but you have to do way in advance, and you have to characterize how much you can do with that, right? So bottom line is that we cannot respond at this point on a 1 year, let's say, time scale for impact. People say, oh yeah, but launch some, but they found that for the problem that we discussed, that it's not going to be effective. So anyway,
And do you think there's something we can do on ground? Let's say we discover tomorrow that in 6 months, 100-meter asteroid is going to impact.
You're talking about, let's say, 200-meter asteroid? I don't think we can do anything.
This on the web.
Sorry. What do we do? That's a problem. Again,
we move everyone.
Yeah, of course. The best that you can do is try to predict where and estimate the impact, casualty, the impact, the damage, potentially. But it's always uncertain because it's like it's always last minute type of thing. So, I'm not trying to be alarmistic here, but reality is that these events anyway, they're not that common. That can happen. But my opinion, people might have different opinions. I don't think we have any direct defense for something on a short scale. Again, as I mentioned, some people say, "Oh, just launch a bunch of nuclear devices, It's just not effective. They've been studied. That just simply you're not gonna be able to disrupt it. You may break it a little bit, but it's not gonna. You're not gonna. The only way to do it is from the inside, blow them up, and And
we can do. We can learn something from the HER mission, right? About this.
Yeah, of course. The more we do, the more we learn. But again, as I said, we don't have a proven means a TRL-9 technology release line that already flew there. We know confidently that we're going to be effective because we never did anything like this. So I'm pretty sure that we're going to try to do something on a short-term scale, but if you ask me, do we have a proven way? The answer is no.
Today, no. To conclude, can we talk a bit about your working as a researcher about there's so many different topics now to handle academic community revolving around you?
Well, yeah, I have a relatively good-sized group, right?
I could see you have like 4 journal papers just for 2020.
Yes.
And
Well,
it's just February, so.
well, there are a couple of more that have already been accepted, but they haven't. Well, again, first thing that is important I want to mention that my lab is called Space System Engineering Lab. I have about almost 10 graduate students, PhD students. And the key part is that when you get to a position like mine, actually one of the frustrations of my work, believe it or not, is that you have less and less time to really actively put your hands, for example, on a computer, on a computer and do yourself, some of the coding. I'm still doing it. I'm still hands-on, and the reason is because I do quite a bit of work on deep learning, on cognitive systems, on application to GNC, and especially for deep learning, there is a new way of methods that borrowed from the computer science community, and they are running in time. And if you don't know how it works, right? Clearly, if you don't have your hands on, it's really hard to teach and advise students. So I'm still spending, I would say, 2 hours if I can a day to just do Python-based codes and an application of deep learning directly myself. But the good part is that I have a very motivated team of students, which involves, it's a mixture of, international and American. And actually, as a matter of fact, 4 PhD students that came from there, some from Politecnico Milan, other from University of Bologna, came there to do the master thesis, and then they decided to stay for the PhD, invited them to stay for the PhD. Then I have other US-based system because some of these technicals we work for defense, and there are programs where you need only US citizens for national defense to work on that. So they're excellent group, and they just help me. They follow my directions, and they many times I give them a lot of inputs, but they also come up with their own things, and that's I think it's the most important thing, because at the end of the day we can't, as a single researcher, you're always limited with what you can do. So one of the most important things is having a very good, motivated research group, especially PhD students or postdocs, and they can support your vision. That's the first thing. Second thing is that to get large number of graduate students, you have to have quite a bit of funding. In the United States, graduate students cost quite a bit of money. I'm talking about $70,000 a year, including overhead and everything, to support one graduate student full time. Okay? So that's the kind of things that then, of course, you have to have the ability to bring the money into, right? But to bring a substantial amount of money, it's extremely hard if you work as a single principal investigator. If you're by yourself, you can write proposals, of course, to different agencies, including Air Force, there is DARPA, the defense agency, there is NSF, there is also NASA, and so on. But as a single investigator, you can bring a limited amount of money, right? So the key part is to collaborate with people. So what you have to do is to find a very good number of trusted collaborators, both in academia and possibly in industry, if you can, where you establish very functional working relationships. Okay? Because another important key part to be productive is that you get along with people. I wouldn't say get along, but you get things done and you don't waste your energy in a lot of personal personal conflicts or issues that can arise especially in academic environments where there's a lot of egos going around, right? So it seems to be kind of originally an overlooked concept, but more and more, even in NASA mission, I've seen people be oriented to having teams that are not necessarily, they do not need to be the best per se, but they need to work organically, and they need not to be disruptive. Otherwise, life is miserable for everybody. And so that's a key part, and it will hamper your productivity. Okay, so it's a combination of things. It's a combination of having, at the end of the day, a right group of students under your laboratory if you work in a university, having a network of peers where you can work together with, and they trust your vision, they share your vision, right? They're willing to help, and they're willing to be team players, with the idea that if you work together, you can do much more, right? And then, of course, you have to have also another important thing that unfortunately I never teach in graduate school. Right? At least maybe things are changing, but this is something that when you go and do a PhD, usually you focus on your research and you become the expert probably in the world in that part of dissertation that you do. But the real life is that at the end of the day, when you get out, you have to write proposals, you have to understand the politics, you have to understand actually the landscape, the funding that are done, so that you don't go after research that is maybe of interest to you per se, but it might not be something that is fundable, right? So you have to have some management, and political, so to speak, capabilities that unfortunately is not taught as part of the PhD students. Even the simple things of how do you write proposals is important. Having, for example, an advisor of helping that can get you into the mindset of how you write a proposal for a successful grant, is extremely important.
Is this something you're teaching your students?
Yes, actually, the way to do it is because I need help too. If you want to write more proposals, right? It's one of those things. It's a little tricky because usually what you can do, you can ask them to write something, and of course, if they don't have experience, it just won't work. So what happens is that you can take that material. It's some good basis, and then you have to phrase it in a way. But then eventually, as you go, if they stay with you, sometimes, usually through their life, maybe the first one are not that great, but then they start understanding how you structure things, how you think about it, and they got better and better and better. That's what happened with me with my advisor when I was doing my PhD. I had no clue at the time. Actually, I didn't even know you had to write proposals, to be honest. I mean, I was, whatever. I was 25, 26. Because I thought, write papers. What is proposals at the time, right? And it was interesting because he said, write a proposal for, help me to do ABC. I had no clue about how to do it, but it just pushed me in there to do it. And then eventually I quickly realized that that's the way to go about it. That's the way you need to do it. It's a vital tool. Right? Because at the end, if you want to just, I wouldn't say survive, but strive, not thrive in the environment to be successful. You have to know how to do this. You have to know how to collaborate with people to write proposals. You have to share ideas. It's a combination of skills that go beyond just a simple write a paper because I did this research and I found this result. So this will affect. Anyway, I hope I gave an idea about how more complex is nowadays doing research, that will respect at least what I was thinking naively 25 years ago about what was research about.
Yeah, for sure. It's helpful for me at least to know about these things.
Yeah.
Thank you very much for your time.
Okay, my pleasure. Thank you.